We'll continue from where we left off. I'll do a recapitulation of what we did the last time. We got to this point where we maximize the variance covariance matrix. And then we indicated that the goal of PCA is to maximize the variance. And in order to do that, we use a Lagrangian function and then generated our eigenvectors using the Lagrange multiplier. And we're able to come out with this differential and got this result. But we saw that this result was a very powerful result because it contains both the eigenvalues and then the eigenvector, which is a U1 in this particular example. And we indicated that from our knowledge of eigenvalues and eigenvector, the lambdas are the values and then the u's are the vectors. And when we pre-multiplied it, we got to know that it will eventually lead to the eigenvalue. And this result was an interesting result, which we indicated. Now, please remember in all of this, I use X and I use Z. I use X when the data has not been standardized. Please take note. I use X when the data is non-standardized or when the data is normalized, I should say. Now, in this very example, when I use Z, then I'm using the Z for the standardized data because one of the things about PCA is that you have to standardize the data. Okay. So I want to put that one across. So we indicated that we have to now find the principal component. Now, what is that principal component? Remember, the principal component is a combination of the original variables with the hope that you will not lose some information. So you are combining X1, X2, X3 up to XP, and then you don't want to lose information without loss of information. And so that you'll be able to indicate that maybe X1 and X2, let's combine it into Z, and then X3, X4, let's combine it into something else. So that is a principal component. So the principal component is more or less like the latent features of the original variable. And we indicated that in order to actually do the principal component, we need to use a method in matrix known as a single value decomposition. Now, what this method basically does is that it helps you to factorize or to decompose the matrix. Now, if you can remember factorization, factorization is more or less like the opposite of expansion. So if you have, and I hope you guys know it, if you have something that is like x squared plus 2x, okay. Now, since x is in both, you can bring x out and then put into bracket x plus 2. I hope you get what I mean. So that is how to factorize. So you are bringing something out from something. So single value decomposition is just application in PCA, and you use it a lot in PCA or principal component analysis. We also use it in image processing. Okay. Yeah, some of you might do that. You also use it in noise reduction of an image. And when you sometimes have an image and the image looks blurred, that blurriness is the noise. And you can use that SVD to lower the blurriness. You can also use it in climate studies, weather forecasting, and things like that. And Netflix has used it a lot, you know, in their work. They've used it in the winning solutions of, 1 million recommendation systems. And I hope that you guys will do recommendation system, because recommendation system is a very powerful approach, which Netflix uses. So when you watch a movie like comedy, Netflix detects that you like comedy. So automatically, when you open your Netflix, it will recommend similar movies for you. Sometimes Netflix will say that because you watch this movie, these are movies you can watch. Why did they do that? They use that to make you stay, to become sort of addicted to the movie. But what you don't know is that artificial intelligence algorithm behind the scene is called recommendation system. And recommendation system uses single value decomposition in this work. So what basically does this SVD do? It transforms variables that are correlated. And you guys remember that we said that you cannot do PCA on uncorrelated variables, orthogonal variables. Okay. The variables must be correlated with each other for you to combine them. So what you are doing is that you're transforming these correlated variables, you're combining them into a set of uncorrelated variables. So when you get PC1 and you get PC2, there must not be any correlation between PC1 and PC2, because PC1 and PC1 alone is a combination of several things, maybe 2 or 3 things. And PC2 is maybe a combination of 4 or 5 things. And those 4 or 5 things were correlated before you combine them. So that is the SVD approach. It's similar to the collective decomposition that we know. So what is this SVD? Okay. What it does is that it factors a matrix A into a product of 3 matrices. So with that knowledge, you will notice that our variance covariance matrix here has been more or less, or is more or less, a product of 3 matrices, U, S, and then a transpose of V. What do these mean? Well, the U is a column matrix. The V is a column matrix. Both of them are orthogonal unit vectors. The S, which is the last one, is the diagonal matrix. So remember, these are column matrices, column matrices, column matrices. So when you take the column matrix of U and V, they make up the eigenvectors of the variance covariance matrix. Okay, so the U make up the eigenvector for the sigma, the transpose of sigma. And then the V is there's a transpose of sigma multiplied by the sigma. This I'm told you guys have already been taught. That's why I'm applying slightly. That's why I'm not going to go into the details for single value decomposition. So once you have this, then you will have the diagonal matrix, the entries in the diagonal matrix S. And when you look at it here, you see that the S is the diagonal matrix. Those entries are the singular value. Here are the singular values of this, which is the lambda. Okay. And of course, they will make up the eigenvalues. And these are the square root of the non-zero eigenvalues of what you see in the matrix itself. So we're going to use this SVD to do our work. When you use it in the case of principal component analysis, you are going to get the weights, which is a use. You can use the SVD to get the weights, which are the importance attached to each variable before you combine them. The U's are obtained by finding the single value decomposition of the sigma. So basically, when we say that you are going to do principal component analysis, it's just a matter of doing SVD, basically. So we're going to use this SVD and then decompose that matrix into 3 parts. And this is where we will land when we decompose it into 3 parts. We are just going to replace it, and you see that very soon. Okay. So you have this what does the U do? The U undertakes rotation, the S will do scaling, and then the transport of X will also do rotation. So first, what we're going to do is that we're going to find the eigenvectors of the sigma and transpose of sigma. Right there. Now remember, I'm using sigma and transpose of sigma because I'm under the impression that we have not standardized the data. But if we standardize the data, then I'll be using R and transpose of R, because by then we are dealing with correlations and not dealing with covariances. Okay, remember that we started with these covariances, but you should know that, because covariances do not have magnitude and directions, we use correlations. Okay? So anytime you see R and R transpose, that is a correlation you are dealing with. Anytime you see sigma and sigma transpose, we are dealing with the covariances. So we're going to use that to generate our eigenvector. How do you do that? So we are going to generate our first principal component. Now remember that the first principal component, P1, is actually the weight multiplied by the original variables, X. That's the first principal component. So if you have your X1 variable here, X2 variable here, X3 variable here, and all of that. Okay? And then you have the observations there. And each one of them has got numbers. Okay? And then we decide that, based on our principal component, we think that we can combine these first two variables. Well, the principal component 1 is going to have these eigenvectors, the U, multiplying the original variable. So it's taking a kind of a portion of each variable, and then combining them into that P1. Okay. Now, how do you get back? Suppose you have the principal component. Okay. How do you get back the original variables? Now, why would you even want to do that? Well, the thing is that the first principal component, okay, might not be able to explain 100% of the data. So let's say that the first principal component explains, say, 95% of the data, which means that 5% is not explained by the first principal component, which means that it will be shared by the others. Maybe the second principal component will take all, or the second and the third principal components will take the 5 and share. But then when you come back to the first principal component, if it is explaining 95% of the data, and now somebody says, well, this principal component is actually latent. I don't see it. What I see is the X. Well, you can get back the X. Okay, when you look at it here, if you even decide to divide both sides by U, okay, transpose, okay, you can now get back the X as being the U multiplying the principal component. I want you to keep this in mind. But of course, you should also note that when you do that, this new variable will not be equal to the original X. Why? Because that 5% part is gone. What you are generating is the one that was created by the 95%, which was the principal component here. I just wanted to know that before we even proceed. So principal component 1 is base weight multiplying by the original variable. Principal component 2 will be the same, the weight multiplied by the original variables. And when I say original variables, I'm talking about all of them, okay, all of the original variables. And then, of course, you can do principal component 3, component 4, all of that. Now, the original variables, I'm using, again, X, because we are dealing with covariances, okay, which is the sigma here. But when we have standardized the data, then the X becomes like the Z, okay, because by that time we are using the correlation matrix. So take note of this. So why would you even call a particular combination a principal component 1? Well, the reason why it's a principal component 1 is because it explains majority of the variation in the data set. That's why it's principal component 1. But how much is that percentage? What is the proportion of the variance explained by the first principal component? Now, let's assume that we have principal components as many as R, okay, such that the lambda 1, lambda 2, lambda 3, all the way up to R, they are sorted eigenvalues. So these are the eigenvalues. Okay? And each of these eigenvalues have got their corresponding eigenvectors, which are the U's. If this is the case, then we can say that the percentage of variability explained by a particular principal component, let's say the first principal component, but here I'm calling it the ith principal component. That percentage of variability explained by the first principal component, if it is a first, then it's going to be lambda 1 over all the lambdas. That is the eigenvalue, okay, of the variable divided by all of the eigenvalues. So that's this percentage is a proportion of variation explained by the first principal component, where the I is 1. If you are looking for the second principal component, what is their contribution? The I changes to 2. And so you can have lambda 2 over all the lambdas. We are going to apply this to our data set. And we are going to find out how many percent of variability is explained by the first principal component. And if we are comfortable with that percentage, then we don't even look at the second principal component. Okay. But if we are not comfortable, we will add the second principal component, making it a cumulative proportion. If you're not happy with that, we'll add a third principal component, making it another cumulative proportion until we are comfortable with it. But note that most of the time, the first principal component and the second principal component will do the job, unless the variables are so many, which is also possible in real life. Let's go back to our example. You will understand this better. So in our data set, this is a data set, by the way, the X's. We are going to cut down these X's, which have been standardized here. You can see that they have been standardized. Oh, by the way, I hope you guys remember how to do the standardization. Do you remember how to do the standardization? Do you remember that Z formula that we used? I hope you guys remember. Do you? Yes. Okay.
Yes, please.
Okay, good.
Yes.
So this data set was standardized. You should know how to do that. So if I give you a small data set and I tell you that this is a non-standardized or the normalized data, I want you to standardize this data to that. That will mean that first of all, this is a data, by the way, this is a variable. It means that first of all, you need to find the mean, and then you need to find the standard deviation. Okay. And then for each variable, you subtract the mean divided by the standard deviation. And then you can now find for each one of these, which should, of course, be equal. This is called scaling. This is called scaling. And this will convert the use of covariances, which are the X's, to the use of correlations, which are the Z's. Okay. So now we have standardized the data here. What is the next thing to do in the principal components? Remember what our goal is. Okay, somebody is asking the question, do we always use the population standard deviation, or we can use the sample? Sample, because as you can see, this is a sample. But I'm writing the population symbol, okay? I'm writing the symbol for population because normally ideally that is what should be. But in real life, we don't have that. Okay. So use the sample standard deviation. I hope that answers your question, Marie. All right. Now, so what we are doing here is that we are going to generate the PCA. And after the PCA, what will come out okay, will be different. And you can see that, for example, it's even different from here. The standardization alone shows that the Z's are different from that. So the principal component, what you are going to get will be different from the original data set. And the resultant, we are going to call it latent features. Latent features. Okay, we're going to do that. And please, that latent features is not the Z's. Oh, I want you to know, it's not the Z's. The Z's, what they are simply doing is that they are just scaled factors. Scaled. But I'm talking about the principal component. So suppose eventually we have principal component 1 and then principal component 2. Let's say we have eventually only 2. And then we have some numbers here. Let's say 0.34, blah, 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 for the first observation, for observation 0 here. Okay. And then we have some other numbers for observation that. These numbers, these information will become the latent features for the original variables, where the original variables this time will be the Z's, the scaled factors. All right. So the first thing normally we do after getting the Z is to find your variance covariance matrix. But because we are not using the X's, we are going to use the Z's. So what we are going to find is rather the correlation matrix. Okay. So that is first thing. And we did this last time. Okay. We found the correlation matrix. And again, how do you find the correlation matrix? Remember, we were using the variances and then the covariances. And you remember there was a formula for finding the variance and the formula for finding the covariances. Okay. The variances are the ones in the diagonals. That's from left to right diagonals. And then the covariances are those on the off diagonals. And because this thing have been beautifully scaled, we indicated that the correlation is the same as the transpose of the correlations. Okay. So we use this Z and we come out with this one. Now, how do we now get to do PCA from here? It's fairly simple. Okay. First, we have to form the R and transpose of R. That is the matrix of the correlations and the transpose of the correlation. Now, if you check on the right here, how you do that in R software, it's quite interesting. I'm using R and R. So when you use the R software, that multiplication is basically done as R percentage times percentage transpose of R. Okay? That's how you do it. And it will generate some values for you. Don't worry, we'll do the same thing in Python. This is what you get. Okay, so what you have done is that you have multiplied R by the transpose of R, and that gives you this. So you now get this. Remember that PCA is done on this. Okay, PCA is done on this. This is where you got to use the single value decomposition. Now, if you are doing it in R software, and again, when you use this once, and we are going to do it, so don't worry, practically. When you use the R software, this is how you run it. You use SVD into bracket, the particular correlation matrix you have. That will give you the answers. If you are using Python, you can give it a name. Say, I want you to pull out the U, the S, and the transpose of V. Okay. We know this first and the last one, they are for rotation. The S is for scaling. That's a diagonal matrix. And then you say it is equal to SVD, which is a single value decomposition. Then into bracket, the R, which is a correlation matrix. And then you indicate that you, of course, want a full matrix. When you do that, you're going to get a value for the U inside this matrix. In fact, ideally, I'm using sigma here, but you will know by now that it could be R. Okay. And this will have its eigenvectors in a particular descendant order I'm about to show you. So when you do that, when you use this SVD, you're going to get the following eigenvector. That's a U, the capital U, Okay? You're going to get this in a matrix form. So these become the eigenvectors. And again, when you go and try your SVD, you can do this. Now, these eigenvectors, the first column, because they're in descending order, the first column will be the eigenvalues, the first eigenvalue. That is the weight assigned to create the first principal component. The weight assigned. So what I mean is that these numbers, negative 0.62, negative 0.65, negative 0.42, okay, they are the U1. And what we will do is this, watch it. We will take that U1 and then we will multiply that U1 by 1.6, 1.7, 1 point that, and then we'll be able to get the first principal component. That's how you do it. Okay? And I'm going to do that with you, so don't worry. So you get this U, okay, where the U1 is the first one, that's the weight assigned to the first principal component. The U2 is the second one. Then the U3 is the third one. Okay. Of course, these are the eigenvalues, so they will have a eigenvectors, which is the next one. And then the these are the eigenvalues. These are the eigenvalues they use, okay, which will have the eigenvectors. Now, the eigenvectors are going to be equal to this. And I'm going to show you how you got that. Of course, when you use the software and you run the above one that I did, it will give you all of it. Okay? It will give you the U, it will give you the S, it will give you the VT. And this S, okay, the diagonal matrix, they are the variances. They are not the standard deviation. Take note. They are the variances. If you want the standard deviation, and these ones are the lambdas. If you want the standard deviation, you have to take the square root of each one of these. So the interesting thing about Python is that Python rather gives you the standard deviations. Okay. The standard deviations is what it rather gives you. So that if you want, of course, the variance, you have to square the standard deviation to get a variance. If you want the R gives you the variances, so you have to take the square root to get a standard deviation. So just so you know, okay, just so you know. So these are the variances. Now, what do these variances actually mean? That is because these variances are what we are going to use to know the contribution of principal component 1 towards the entire data set. So how much is the contribution of principal component 1 towards the entire data set? We are going to use these variances to do the computation. How do you do that? Well, we said it before. Check it here. So let me just go back here. That if you want to know the contribution, you just take that lambda, particular lambda here. Don't forget this one. And then you divide it by all of the rest. Now, how many of the lambdas do we have here? The variances there. We have 3. So if I want the first one, I'll take the first one, lambda 1, divided by the 3. I will know the proportion of variance, explained by the first principal component. If I want the second principal component, I'll take the lambda 2. And where is the lambda 1, lambda 2? They are the ones on the S diagonals. Okay, they are the ones here. So I take this one. So I take this 5.077 blah, 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 okay, divided by the sum of all these diagonals. So that's what I want to do here. So I've done that here. Look at it. So I take the 5.07755 divided by all these diagonals. Remember, the last one is almost 0. If you look at it carefully, okay, 0.40, so it's almost 0. Then whatever you get, you multiply that by 100%, and that will give you 90.27%. What does this mean? This means that the first principal component, because this is, I use the 5, first principal component explains 90.2% of the data set. So the first principal component alone gives you almost all of the information you need. So that variable Z1, variable Z2, variable Z3, the first principal component alone, the latent features alone explains almost 90% or 91% of the data. What about the second principal component? If you want to find the second, take the value. I've done it automatically. Okay. You take this 0.547 divided by all the lambdas, and that will give you 9.72. So if you watch it carefully, there's some slight loss there. Do you realize that? So for example, if you add the 90.27 to the 9.72, you are going to get something like 98 point something. Of course, rounding is up. And then this very one takes approximately 0, the principal component 3. So we will not need principal component 3, obviously, from this example. The question is whether we will even need the principal component 2. We'll check that because there's something we call the elbow effect, which will guide us to do that. Okay, so now we know the contribution of the first principal component. Now, if you solve this thing in Python, and we'll do all of this, don't worry. Okay, if you solve this thing in Python, you will be able to use Python. You'll be able to use this approach down here, okay, np.sum, to be able to get each principal component percentage. Now, how do you get a principal component? Because remember, principal component is more or less an equation. It's like a regression equation. And in a regression equation, you have the y, okay, which is a function of, let's say beta 1, x1 plus beta 2. I've just ignored that intercept. Beta 2, x2, and then on and on and on. So these are more or less the original variables. In our case, the z's. Okay. And then the beta 1 and the beta 2 are the weights, which in this case are the u's. Okay. They are the u's that you are dealing with. The u1, the u2, the eigenvector. Now, how much is the contribution of x towards y? Well, in regression, we look at the marginal effect of x on y. Okay. But the key point is that if I want y, all I have to do is I combine these ones and I'll get a y. So if I want the first principal component, I'll take these weights, multiply it by the original variables, and then I'll get a principal component 1 based on their percentage contributions. Don't forget. So now we are going to calculate each principal component. Remember, we have the original variables. Let me show you the original variables. Yeah, here. On the top right here are the original variables. Okay. On the top right here, we have the original variables for each one of them. So original variables are Z1, Z2, and then Z3. Remember, these are standardized, okay, which is a whole new thing we would have done before coming to this level. And these original variables are more or less like the x's here. Even though I'm using the x's, they're actually the z's. Now, if you have this in mind, you would then understand that if we take a matrix of all the original variables, the x's, that is this. And then we can now, because remember, because we are calculating the principal component 1, we can now say that U1 transpose will multiply each of the x's. And it's true, U1 transpose. So whatever you see here is U1 transpose, just that you are multiplying it by which particular variable. That is why you have the exponent. And I said already that since the x's here have been standardized, okay, sometimes I'll use the word z. I shouldn't be bothered about that. Z is just the standardized data. So we are going to calculate for observation 1, what will be its principal component. Now, this is observation 1. Okay? I'm calling it 0 here because, Python normally will start from 0. Okay? Or let's say observation 0. So these are the observations. Okay? There are 4 observations, 0, 1, 2, 3. So for this observation 0 or observation 1, which I know you understand what I mean. How do we get a principal component 1? Well, to get a principal component 1, this is what you do. You would take each of the, remember, as you can see here, it's multiplying each variable. Okay. And this x1 variable, I've renamed it as z. So just so you know, because you have standardized them. So you take each one of these and multiply it by the original variables. Okay, this is a matrix. So each one of this is what? U1, we already knew about it, okay, from the previous. Okay, we knew that U1 was negative 6, 2, blah, blah, blah. U2 was negative 6, 5, blah, blah, blah. Okay. U3, sorry, U1, 1. Okay, U1, 1 was negative because they are all 4 for U1. Okay, U1, 1 is this, U1, 2 is that, U1, 3 is that. So we take each one of these and then we multiply it by the original variable for observation 1. Don't forget. So we are just taking the first one. And you're going to get one single value. Okay. As you can see, it's here. Okay. If you multiply this one by this one by this one, you're going to get one single value. And that one single value is 2.47 million. So that is the principal component 1, for observation 1, for the first observation. Now, for the second observation, you are going to use the same weight here, which are this, and multiply it by this second observation, which is this. And that is going to give you 0.640 and on. So what does this mean? What does this first one we've done here? What does this mean? Of course, we know it's a principal component 1, but what does it mean? It means that this first principal component, this negative 0.27 blah, 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 is a linear combination of, that word linear is not really clear. It's a weighted linear combination of the original variables here. Okay. So this one is a weighted linear combination of the original variables. And this accounts for the largest variables, okay, that we have. You can do, and we've done it for the first observation. You can do it for the second observation, which is here. Okay. And this second observation, of course, is also a weighted linear combination of the original variables in the second observation. Then you can do for the next observation and then the next observation, okay, for all of them. You can do that. Okay. I'm going to show you. If you try your hands, and you should try your hands on this. If you try your hands on that, you're going to get something like this. So you do that. You try your hands on that for all of them. Then you go to the second principal component, because this is the first principal component. Okay. You do it for each of the variables. Then you go to the second principal component. For the second principal component, you are going to use these values. Okay. Just go up here. You're going to use this U2. Okay. So you're going to use 0.37785, 0.2172, negative 0.99. You're going to use this one and then multiply it for each observation, for Z1, Z2, Z3. For each observation, observation 1, observation 2, observation 3, you do for all of them. And then you're also going to get what you see on the right here. For the first one, observation, you're going to get this one. The second observation, you're going to get, and you're going to do for the third observation, then you do for the final observation, which is the fourth observation. If you do that, you know what you're going to get? You're going to get principal component like this. So now we have the following principal component because we did it for. So we now have rearranged the entire Z value into sort of principal components. And so we have principal component for the first observation, And this was what we calculated. For the second observation, of course, in an exam, I'm not going to ask you to calculate for, principal component 3. I might ask you to calculate for principal component 1 and principal component 2, and maybe for some particular observations. But you got to just learn how to do for this. So this is like you have replaced the original Z variables with these principal components. So these principal components now, but we know what this one is. This one, how much contribution it does, This one, how much contribution it does, you also know that. If we decide that we are going to select only the first two principal components, which we can because the first two explain almost 98% of the original data set. Then we cut off the last one. Okay, so we are left with this one. So we're going to focus on this. But if we decide that we're going to take the first principal component instead of the first and the second, then we are going to be left with this. That becomes our variables that we are going to use. So normally you do this thing before you do a regression. So maybe if there's a problem of multicollinearity, you combine these three variables into one like this. And you're fine with this. You go and use this one in your regression, which will capture the whatever you want to capture because it has removed all the correlations. And then now what you have is orthogonal. Okay. Everything that I did, I've given you the pictures here for you to do it in Python. So you should be able to do that. And I'll do that with you today if there's time. Now, we have been able to get what you have here. Watch it. What you have here is very interesting. We have new variables replacing the original. Now let's go to the original and then you see. This is very interesting. Look at the original. I'm just going to take the first two. Look at observation 0, or the first observation. The original variable, and when I say original, I'm talking about the standardized. The original variable here is 1.627. The second one is 1.7. Okay. And the last one, of course, is 0.8167. Are they the same thing as we have here? Let's look at what we have here. The first one is 2.47. But if you can remember, the original was 1.6 something, 1.62. Okay. And then this second one is 1.7. Okay. So the question is, one may argue that these principal components are not our actual data set. That's what one may say. They are not our actual data set. They are different from the actual data set. And then you tell the person, but we can get back our actual one. We can get back. Which actual one? The one I just used was not even the one that you should use. Okay. We can get our actual one, the non-standardized one. I know that one is far. I can't go far like that. But you know what I mean? Okay. It started with 70 and things like that. We can get that actual one. Oops. You can get that. How do you get the actual one? Well, this is how you get it. This is how you get it. I've told you before, some few minutes ago, I told you that that formula can be changed and you can get back the X, if you can remember. Okay. The principal component, which was P, let me just remind you here. The principal component, which was P, was equal to U, transpose X, if you can remember. Of course, we did it for principal component 1. And on the basis of this, if I want X, we can use the principle of change of subject, remembering that these things are not actual values, but they are matrices. Okay. And so even if you divide both sides by this, when it comes up, it becomes no longer a transpose. And so our X is going to be, that. So that becomes our original X variable, which is what you have here. So we can use this formula, it's like change of subject, and get back our X. So for our observation 1, okay, if you want to get principal component 1 and principal component 2, we can use this. So if you want to get a Z value, of course, this X is like a Z, like I told you. If you want to get it back, you just take each of the weights here, multiply by, and you can see it here, is the weight here multiplied by the principal component. Okay, and then the other one, you take the weight again, multiply by the second principal component, and that will give you the original Z value. So let's see whether we can get the original Z value for just for the first observation. The first observations are only 3 variables. Okay, that is Z1, Z2, and Z3. So we take this very one here, which is the weight, multiply it by the principal component, which is that. Then you take the second weight, the U's, you multiply it by the second principal component. Oh, this one should be multiplication, yeah? I should have removed this. It should be, this one shouldn't come. Okay, so you take this one, multiply it by the second principal component. Okay, and then you add them. And in a matrix, when you are multiplying and adding, you know how to do that. You add them, and that will give you this. You get 1.65, 1.67, and then 1.821. So this should meet the Z values that we had before. The question is, do they meet it? Let's go and check the Z value. Remember, it's 1.65, 1.67. Okay, but the Z values, where are they? These are the Z values. We don't have 1.65, but it's close. Okay, the other one was 1.67. Here we have 1.70. Why the difference? Well, it is still correct. Okay, so this is 1.65, 1.67. Look at the last one, 0.821. Okay, but when you go to the original Z and you check, it is 0.816, almost 0.821. Why the difference? The difference is because we have not included P3. Remember that we have P1, P2. So that P3 is the loss of information after the dimensionality reduction. Loss of information after. So you have been able to get back the Z values for the first observation. That is a standardized. Okay. Now, how do we get the non-standardized? Well, let me just remind you. Remember, we got it as Z equals to X minus mu. You said we should use the sample, so I'll use the sample divided by that. And if you are using this, you have to also use the sample, which is X. Okay. So how do we get back X? To get back X, you multiply this by that, isn't it? So if you want to get back X, X will be equal to, and then you will have Z sigma plus X bar all U. So if I want to get my original variable, I'll still use this formula to get back the original variable. How do you do that? Well, you take each one of them, and then you can multiply and then get back the original variable. And that original variable is lambda. Okay. So it means that you must know the standard deviation. Okay. You must know the current Z value. And these are the Z values. And then you must know the means, which you already knew that. Okay. And with this, you can multiply it and get back the original variable. And when I say original variable, I'm talking about the one that started with the 70 point that, 200 point that, this one point that. You can get back everything. So the analysis is just to compress and give you, lower everything down to a principal component that makes practical sense. So that is how you run all of these analysis. Okay. So this is what I have given you. To get back the non-standardized, you use this formula to be able to get it back. Okay, that's it. Now we are going to go into Python, and then we'll see how this was all done there. So look at this Python command. Okay, I'm going to start from here. And guys, you can, I've given you all the commands in the slides. So I'm not supposed to even give you this. I wanted to kind of type it yourself. That's why I've given it all of them to you in the slides so that you can type it yourself. Okay, Lieza says, confirm for me if we use the standard deviation and mean of the original data set. Yes. The standard deviation and the mean, yeah. Okay. Now, let me get it right. You would have, if you have used the Z value, the data set for Z value, okay? If you have the standard deviation and the mean for the Z, that's what you're going to use. Because you are using the Z and you are trying to get the X. So you use the standard deviation and the mean of the Z, the standardized data. So when you use the word original, I didn't know which original you meant. By original, you're talking about a Z, yes. By original, you're talking about an X, no. All right. I hope, Eliezer, you get me, Christian. Perfect. You've replied. Okay. So now, guys, to do the whole thing in Python, you just run this first command. Okay. What are the packages? You need NumPy. You need pandas. Okay. If you want some graphs, and we shall show some graphs, you need Seaborn. Okay. You need matplotlib and the .pyplot. You need some libraries for building the regression equation and the models. Okay. So these are some other packages that you need to be able to use for this. And you will notice that this is key. For example, this one there is key, the standard scalar, okay, and the minimum scalar. These are good for the scaling. That is why we've loaded it. Okay, and then I brought this one here, numpy.linalj import. This is for the single value decomposition. So let's load the data. What is a data set? The data set is what you know. Okay. So I have my data set in a CSV file. I load the data set. I'm going to load it here for you to see. Good. Data set has been loaded here. To see the data set, you can just run D. And then there you go. This is the data set. And you all know this data set. Okay, this is original data set, 70.2265. This is original. And then the last one were bigger numbers, if you can remember. This is it. So I've loaded a data set. This data was just like this in Excel. The only thing is that the first observation is now 0. And the fourth observation is now 3, which you know why. I can now standardize this data easily. And you can use this command to standardize the data. So you can say that scalar.standardize scalar into bracket. Okay, this will standardize the data. And then I decided to rename the data. Remember, it was called D. I decided to rename the data as DF. So I'm now calling the same data DF, but it's not a standardized. It's not a standard. And watch this. Python didn't help me. It helped me fantastically, but it didn't help me with something slight. What it did is that it gave me everything. This is a standardized data, and you guys can remember. So remember that whole Z formula you are using for this. It gives you everything, but it is still calling it what? X. So I don't want the name X. I want the name Z. So I said, this DF data, I want you to still call it DF, but I want you to rename the columns X1 as Z1, column X2 as Z2, and column X3 as Z3. So I do that and run the results and show the results. It's the same as this one above, and now the names are properly shown. Fantastic. So you now have your original data, or you have your standardized from the non-standardized data. This is the data we are going to use throughout. So with this data, how do you work it? Okay, so we are going to jump from here, and then we are going to create a correlation matrix of the data. So I come here. Okay, forget about this one. I come here. I indicated that I wanted to generate a correlation matrix of the data and call it correlation matrix A's and print it out for me. So let's run that. Okay, so it looks like, let me just run this one. It looks like I didn't run it. Oh, let me rename it first. Okay, so sometimes it happens. So when you have the data run like this, and then you run your correlation matrix, yeah, it should perfectly work. So this is the correlation matrix which we generated, and you can see that the diagonal elements are all 1, 1, 1, 1, 1. Okay. Now remember, this is R. I called it R, not sigma. It's R because it's based on the standardized data. Cool. The next thing now I wanted to do was to generate something on the R. What I wanted to do is I wanted to write the correlation matrix in a heat map. You see, one good thing about heat map is that it gives you colors and it also gives you the correlation matrix. So I decided to use this command to generate just a heat map. Okay, so if you look at this color here, it tells you that those that are very yellow are perfectly correlated. And they are still, we are now still using Z because that's on the standardized, okay, which is cool. Of course, the heat map has got different colors. I'm using the varieties. You can change the varieties, and then you can use a different color. Let's say hot. Okay. So when you use the color hot, then you can have a different color like this. And with this one, the whiter it is, the more correlated it is. So you can see that these ones are highly correlated. Z2 and Z1 are highly correlated. And normally those that are highly correlated are the ones you are likely to combine. Don't forget. Okay. If you look at Z1, it's not that much highly correlated with Z3. If you look at Z2, it's not that much highly correlated with Z1. That is just 48%. But if you look at Z1 and Z2, ooh, 98% correlation. So that is where the likely PCA will happen. So no wonder we eventually settled on principal component 1 and 2. Okay. Now, the next thing after generating the R, which is a correlation matrix, is to take the R and multiply it by the transpose of R. You guys can remember. So here, I generate RT, which is a transpose of R. Okay. And you know it's going to be the same thing. So I run this command, and its transpose, you're going to get the same value because we said that for correlation, because of the diagonal element and the answers on the top, if you turn the R into its transpose, you get the same thing, unlike the covariance. So that gives you this. Now, we can find the SVD, okay? The SVD. And I told you that Python uses this one. So I'm going to use this one, USVT, to generate the single value decomposition, which is, of course, going to give us the use that we had. So when you run this command here, which I have done, and then you tell it that I want you to give me only the U. So this is a U. Okay? You get the use value, and this was the same values we had when we were computing. Okay? So this will give you the first column here. First column here will give you the U1. Okay, this one will give you the U2, and this one will give you the U3. And of course, you can use these ones to find your principal component by multiplying each one of them by the Z's. Now, we also indicated that these are the eigenvectors, or what we call the loadings. We also indicated that you can find the eigenvalue, the S. Remember, it's USBT. So here we find the eigenvalues. And you can see that the eigenvalues are this. You remember we indicated that they are the square root of the eigenvalues. The square root of the eigenvalues are this, or what we call the lambdas. Now you remember that the one we found, or rather give us a variance. Okay, but this is giving us a standard deviation. So each one of this is the standard deviation. So if you want the variance, it's simple. And I use this command to find the variance here. But first, let's find the standard deviation. There you go. Then I can run this. np.squares of s is going to give me the variance. So when you run that, there you go. You find the variance of each of them. Okay. Now that you find the variance of each of them, it doesn't tell you the proportion. So now, what is the proportion of variance contributed by the first principal component? You first of all have to add all these. Okay. And then, and remember, this last one is 0 because of the exponent e minus 0.75. So everything here is 0, more or less 0. So you add all of this, then you take the 5.078 divided by the total. Okay. And that will give you that. And I did that. I did that here. Look at that. By the way, note that if it, so that's what I did. You take this one here, divided by the sum of all of these, and that will give you this. So we had 90%. Just do that for it. So we indicated that the first principal component contributes almost 90% of the data set. If you want to find out of the other one, you can just take the other one and divide. If you want a cumulative, you can also use the cumulative. You can do that. Now let's go back to our data set here. Okay, this is our data set. Let's not forget. In this data set, how do you now do the PCA easily? Well, you will use this command known as sklearn.decomposition. And this command will generate, or you're going to see something interesting here. So I'm going to run this command, and you have PCA. So if you want to use PCA, you just, from this package or library, you can indicate that, let our PCA indicate that. Now you can see that I've indicated a number of components I want to extract. I want to use 3 components, but you can change the 3 components to 2. But let's start with 3 components. And then we can use the fit transform to be able to generate our principal component. Okay. So I've just run that. And you can tell it automatically, without calculating, to give you the loadings. Okay. So this command will give you the loadings here. And you can see that these loadings are the contribution of each principal component towards the variable in question. Okay, the contribution. And you can generate the heat map even of the loadings. And you can see that you are able to generate the heat map of the loading. That is a contribution of each principal component towards any of the variables. Okay. And then you can also find the cumulative proportion and then the proportion. So this command will give you the cumulative proportion and the proportion. So for example, the proportion of variance accounted for by the first principal component is this. The cumulative proportion is that. Now you might see that there appears to be some slight difference between this and the one we calculated. You will notice that. The cross-loading, somebody is asking what's that? The cross-loading is indicating the contribution of each variable towards, okay, let's say it is a correlation between the principal components. The correlation between the principal components and the variables. Now, if the variables are 7, the principal components are going to be 7. Now, the correlation between each one of them, that is the cross-loadings. Okay. So that is the answer to your question, Eve. All right, so you will get the proportion as well as the cumulative proportion for each one. Now, how many principal components should we select? How many? Should we select one? Should we select? By the way, these are the principal components, the one we generated in the Excel, the one we generated in the notes. Okay, how we calculated for each one. You command that I want you to get me, each principal component. So these principal components are what are supposed to replace the original variable. So you can use this command to be able to get it. And then finally, something I didn't teach you in the handiwork is called scree plot. Okay, so you can generate this scree plot using this command I'm about to show you, and I will explain what a scree plot is. And of course, this command to also generate a scree plot. When you run this, you'll be able to generate a scree plot. What is a scree plot? The scree plot will guide you to know how many principal components to select. So this is a scree plot. On the x-axis is the number of components. So it's telling you, should I use 1 component, 1.25 component, 1.5 component, 2 components, and then 3 components. Now it is 3 here because the number of variables were 3. The principal components were 3. So the scree plot will move up to 3. Then the top part will tell you the explained variance ratio, okay, the vertical axis. What the scree plot is going to do for you is that suppose you have 14 principal components. The elbow, the burning, the first burn, where it bends is where you will get a guide. It's a cutoff point for selecting your principal component. So let's say that if you look at it, it didn't burn at 1.25. It didn't burn at 1.5. It didn't burn at 1.75. The first burning from the top, the first burning or elbow, if you look at the elbow, the whole thing is shaped like elbow. So sometimes it's called an elbow effect. It's at components 2. So what it means is that this studied, for this very example, the number of components to select is not component 3. The number of components to select is not component 1, but the number of components to select is component 2. And you can see this is another one which we call 90% threshold. Okay. This 90% threshold will tell you at how many percent, if you want 90% of the data, okay, what is the threshold for that? And you can see that the threshold for the 90% is 1.6 thereabout. Okay. But for component 2, you are getting a good, percentage of the data, which is almost like 100%. That's what it's telling you. So these two graphs gives you a sense of how many components to extract from the data. Ladies and gentlemen, this is a practical demonstration of the principal component. I can give you this file so that you can run it yourself and then have a feel of how this works. But it's all in your slides. Okay. So when you check the slide, let me show you something here. When you check the slides, it's all here. The commands are all here. Okay. Everything is even done and copied and pasted. All of them are here to guide you in that regard. Everything is here in the slides for you to be able to get it. So that is how you generate principal component, even including the scree plot and everything is all here. All the codes to be able to get a scree plot are all here in the slides. So go through the slides, work it out, and then you should be fine. The most important thing for what we have done today is extraction of PC1, PC2, and PC3. Your ability to manually work this and eventually come out with the principal component, the percentage of the contribution. Okay, how much percentage does the principal component have on the original data set? That is it. How to convert the original variables into the Z variables. You should know that. So if you have an original variable, how to scale them. Okay. How to be able to do that conversion, and then how to use that correlated variables that Z variable to generate your matrix. And then how to move from that matrix, multiplying that R by the transpose of R, and then going from there, if the transpose of R has been given to you, okay, maybe you don't do the multiplication, but if the multiplication has been given to you, how to now use that to individually, together with the weight, find the first principal component for a particular observation. How to be able to do that. You should be able to know all of this. Right, ladies and gentlemen, that brings us to the end of the entire caboodle. If you have a question, you can ask now.